Hello, Math 8 students. This is Open Up Resources, Unit 2, Lesson 10, Meet Slope. To get started, we have this very quick problem. It says we want you to write some numbers that are equal to 15 divided by 12. Notice what I'm saying. I say some numbers. That means plural. But this is just one single problem here, so how can I have multiple numbers that all answer the same question? Take a second and think about that. Online learners, pause the video to give yourself the necessary time. All right, come back to me. What do you think? How can I possibly have multiple numbers here? Jacob? Great, and I think those are all fantastic. There's different ways of writing the same number. So 15 divided by 12, one of the ways that I can even write that is just writing it so it looks like a fraction. There's one version of that. And as Jacob said, we can simplify that. We can write it as a mixed number. We could write it as a decimal. I even have students in my last class who said that they wrote it as a percent, and those are all possibilities. You do have access to your calculator, so you should be using them if you're struggling with this, but 15 divided by 12, if I simplify this, I get 5/4. If I unsimplify 5/4 and multiply both parts of this fraction by 2, I would end up with 10/8. I could also write 20/16, and there's so many other possibilities and so many other options. Returning to the 5/4 though, that leads us into what Jacob said, a mixed number. That would be 1 and 1/4, which also helps us get it to a decimal, 1 and 25/100. And of course there's lots of other ways, but here's the grand takeaway from all of this. There are multiple ways of representing it, and I want to focus on these ones here. With the grand takeaway, because this is going to be really important in today's lesson, that fractions are friends. And remembering that fractions are friends, you can see that these are all equivalent fractions. There's lots of ways of writing 15/12, starting with the most simplest version. But if I had numbers like 10/8, we would also simplify that to the 5/4, and all of these are equivalent, and recognizing that is really important. Let's move on to the actual lesson. We have here, it says similar triangles on the same line. And this figure here shows 3 triangles, each with its longest side on the same line. It says your teacher will assign you 2 triangles. I'm not going to assign you 2 triangles. I just want you to pick 2 of those 3 triangles. What I want you to do though, for those of you working in groups, I want you to pick 2 different triangles than your partner. So just pick a different pair than your partner, and I want you to complete this activity. Really though, to get you started, I have this applet to kind of show you what this is really looking like. This is kind of the same sort of image, just a digitized sort of version of it. And watch what happens as I move this slider. Now I'm going to go up. How could you describe what's happening here? Logan. I am changing the scale factor, and using that word scale factor kind of gives us a clue what's happening. The scale factor is correct. So this S stands for scale factor. This is a scale factor of 0.25. Notice what happened. This is a scale factor of 1. Notice what happened. This is a scale factor of 1.5, a scale factor of 2. What is the mathematical word that describes what's happening here? Jacob? Yes, these are dilations. So that's one of the things that I want you to take away is when we see this, this applet here, it reminds us that what we're really seeing are different versions of the same triangle. They're dilations, right? So keep that in mind as I ask you to explain why the 2 triangles that you have chosen are similar. When you're finished with that, I want you to start filling out this table. We've got our 3 triangles. Measure the vertical side. Vertical means it's going up and down. Measure the horizontal side. Horizontal means it's going left and right. And then complete that ratio or the quotient, vertical side divided by the horizontal side. So online learners, pause the video until you've completed those things. In-person learners, go ahead and work with your groups until you have made it to this point where you have completed the table. Again, start by picking your 2 triangles and explaining how you know they're similar. Finish up with completing that triangle. All right, let's begin by focusing on our triangles and showing how they're similar. I'm looking for different methods, different explanations of how you found they're similar. Do I have anyone who wants to get us started? Brody, start by telling me which triangles you chose. Okay. Okay, good. So you're noticing that they're dilations of each other if you're recognizing that scale factor. So triangle FGH and triangle ABC. You can see we have a side length here of 2, wrong color, a side length here of 2, and the corresponding side length is 4. And how does the 2 change to a 4? We're doubling it. So here we discovered that this is a dilation with scale factor 2. We can also see this side length here is 1 and a little bit more. I think we can probably say 1.5, double that, and we get our side length here of 3. So we're noticing that scale factor of 3. This is actually something that's really important. Although I do want to take it just a step further to really fully complete this. We want to really extend this to the definition of similarity, which requires 1 extra step. So I'm going to see if anyone else has that kind of an explanation. If so, then we'll go over it then. If not, we'll come back and talk about this one. Different triangles. Let's talk about different triangles and how you proved it. Logan. HGF. Oh, and ABC, so you did the same triangles though? EDC, I'm sorry. EDC, and to keep those corresponding parts together, EDC and CBA. Geez Louise, okay. And HGF. Am I on the same wavelength now? Okay. How did you show that they are similar? Okay. Okay. So here you just compared and recognized that the scale factor was 4, using those side lengths to compare the ratios. Good. Anything else? Any other methods for any other triangles? Think about what we learned in our last lesson. James? Okay. Okay, perfect. And that's extending on to what Brody started. You use the full definition of similarity because you started by translating it first, showing that we can use a sequence definition of similarity. Go from a full sequence of transformations, starting with a translation and then showing that dilation. So to go from FGH to ABC, we had to, I'm just going to give myself a little bit of extra space here. I'm assuming you did your translation first. Is that what you said? You did the dilation first. Okay, that makes it even more challenging because it's hard to identify what that center of dilation is, I guess. Or no, I guess you could probably do it. Did you use this as a center or this? Or this? You don't know? Okay, then let's go back and let's actually do that transformation or the translation first, where we're going to translate FGH. Let's see, how much would that be? Down 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, 8 to the right. Translate or left. 8 left. Down 6. And now that puts that triangle in this position here. And now it's a lot easier to see. Dilation with scale factor 2 and A as the center. If we do that translation first, then it does help us identify that center of dilation a bit easier. So ladies and gentlemen, I want to really focus on this one for just a second. This uses the definition of similarity. The definition of similarity does require transformations. So Brody got a great start by identifying that scale factor, but we want to always go that step further and identify the full sequence of transformations. There are other ways. Thinking about yesterday, we talked about identifying if triangles are similar. We had just 2 pieces of information that we needed to show that triangles were similar. So I want to talk about that. Let's look at triangle ABC and triangle CDE. And yesterday we talked that when we have triangles, all we need are 2 angles. So it should be easy to see that we've got a right angle here and a right angle here. There's one angle. Get out those protractors, measure another angle. In my opinion, the easiest angle to measure would be angle A and angle C. They are the same? You measured them that quick? Nice. Looks like I'm getting a 35-degree angle. And 35-degree angle. And that's all I need to show they're similar. No need to go through all of this whole process. It is a definition of similarity, but really we have a right angle and we have a 35-degree angle. And so that's all that we need. Now, let's return to our table and let's start filling that out. Help me out so that we can get through this quickly. Triangle ABC, vertical side and horizontal side. Give me both of those measurements, please, Michael. Great. So when I'm trying to do vertical side divided by horizontal side, that's going to be 3 divided by 4, which simplifies to 3/4. We're going to keep it 3/4. Yes, you can convert it to the decimal, but fractions are friends for this lesson for sure. Next one, we have triangle CDE. Triangle CDE I'm doing in purple. Brody, give me both measurements, please. Okay. Great. So the vertical divided by the horizontal, 6 divided by 8, which simplifies to 3/4. Yep. And our last one, triangle FGH. Thank you, Lainey. Are you sure? No, you're right. Not 1/2, but 1.5, right? So the vertical side is 1.5. The horizontal side is 2. I'm not going to write 1.5 as a mixed number, though. I'm going to write that one as a decimal. Make it a little bit easier. And what is that one? When we take the 1.5, divide it by 2, what does that give us? James? Yeah, if we type it into our calculator, it's going to give us 0.75, but we should understand that 0.75 is that fraction 3/4, the same as what we saw in all of these other ones. This is actually a really important relationship. This also does help us to show similarity because all of these side links share that same ratio. And that ratio is so important it has a name. So go to the next page. we've got this little bit of space here. This whole lesson, as you might remember, is called Meet Slope. We're introducing a new concept. And to do this new concept, we're tying it back into something that's familiar, our transformations, our similarity, our dilations, and tying it into this new concept of slope. Slope is, I want you to write this down. We're going to write kind of an abstracted meaning that doesn't make a whole lot of sense right now. But slope is the ratio of the vertical length, like our triangles, the vertical length of the triangle, to the horizontal length of our triangle. It's a lot of words, kind of hard to understand, so I'm going to write it a few different ways. And the way that I'm going to write it kind of ties in and relates to the ratios that we observed here. So, the vertical over or divided by the horizontal. And throughout this lesson and this unit, we kind of stop using these bigger, longer words, vertical and horizontal, and we start talking about the rise. Because the rise is that vertical movement. Over, instead of using the word horizontal, we usually use the word run, because the run is that horizontal movement, that left and right movement. I'll also draw it here with pictures. Slope is the up and down, over or divided by the left and right. This is the way that I'm going to refer to it most often. For this lesson, I'll continue to use vertical and horizontal, but pretty soon I'm just going to stick to these words, rise and run. So I want you to really understand what they mean. And I hope that these pictures, these arrows help a little bit. So, multiple lines with the same slope. That's that word from right here. So when I see this right here, this slope, I'm immediately going to be thinking and writing vertical divided by or over horizontal. And we're actually going to start here with number 2, where it says draw 2 lines with slope of 1/2. And here's what I'm going to do with that information. It says slope of 1/2, so we have a fraction already, and slope, as I remember, is the vertical over the horizontal. So having a fraction is incredibly helpful because I can now see that the vertical is 1 and the horizontal is 2. Having it already set up as a fraction makes this so much easier. That's why I'm starting here with number 2, and then we'll go backwards and do number 1. So let's just pick any point. I'm just going to make it simple. I'm going to pick this point here over on the left so that we have plenty of space. And with this point, I need to draw a line. 2 points are all we need to define a line. So I just need to find the second point. How do I find that second point? Well, I have a vertical change of 1. So I'm going to go up 1. And I have a horizontal change of 2. So I'm going to change horizontally 2. There's my 2 points. That's all you need to define a line. Now we actually have to draw the line. And I don't want just a small little line segment. I want a line. So I want it to extend to the edges of our paper. Well, to the edges of the graph anyway. And even better would be to draw arrows at the end to show that just because it stops there at the edge of the grid doesn't mean it's done. Those arrows show that it continues infinitely. Yes, rulers are friends. Definitely have a straight edge. That's why they're in your baskets. Okay, I drew one line with a slope of 1/2. Your job is to do it again. Draw a second line. somewhere else. So find a different starting point. Use that vertical and that horizontal. Draw a second line. And then answer the question, what do you notice? I'll be wandering around the room, checking in on you, seeing how you're doing. Online learners, pause the video until you've drawn your second line. Since we should have drawn a second line with slope of 1/2, we're going to pick a different point. Probably not this one because that's where I started my first line. So maybe right here. And we only need 2 points. This is the first point. To find the second point, I have to have a vertical change of 1. So I'm going to be going up 1 because that would be a vertical change of 1. I need to have a horizontal change of 2. So that means I'm going to need to go over how much? Should I go over 4? Should I go over 7? Should I go over 1? No, the horizontal change needs to be 2. Guess what? I have my second point. All it takes to draw a line is 2 points. So I'm going to draw that line then that goes from here to here. And of course, since it's a line, I'm going to be extending it. Why didn't it make those changes? There we go. What do you notice about these 2 lines? Look at my lines, because many of you had just small, tiny little errors on your paper. What do you notice about my 2 lines that are drawn precisely? Kaden? What do you mean by the same? Because they're in different places, so I don't know if I can say the same. I know what you're trying to say. Let's see if we can have someone who can explain it with a little bit different words. Lainey? They are parallel, yes. They're parallel because what you're saying, Kaden, is you're saying they're both going up vertically. Well, but this line could also be going up vertically too. Is that going to be the same? No. And it's not really just going up vertically. It also has that horizontal change as well. That's why it's not just a vertical change. It's vertical and then the horizontal. So we're looking at how it's changing both vertically and horizontally. Always measuring the diagonals with the change up and over. So what do we notice about the 2 lines? They're parallel. Now, because we struggled with that so much, we're going to do it one more time, but I'm going to show you something else that's going to help you be really, really precise. So down this, it kind of covers the mistake that you made that will make your line even better. We went up 1 and over 2, right? Will you check to make sure that on your line, the next points you're going up 1 and over 2 again? And again, up 1 and over 2. That's how you're going to make your line the most precise. So when you just drew your line like this and then it started getting a little bit off, we can always correct it by making sure it goes up 1 over 2 and again, up 1 over 2 and again, up 1 over 2 to get that level of precision. And now, we did struggle. So I want you to draw a third line, please. Make it nice and precise. A slope of 1/2. Again, I'm going to be wandering. Online learners, pause the video to give yourself enough time to do this. Okay, doesn't matter where you started. We're picking a different point. I would prefer a point that's not already on one of these 2 lines. And again, the vertical change is 1, so that means I'm going to be going up 1. The horizontal change is 2, so that means I'm going to be going over to the right 2. There's my second point. And as I'm drawing the line that connects these points and extending it, I want to make sure that I'm being precise. And I can see I need to go, again, up 1 over 2. Up 1 over 2. up 1 over 2. And so now I can guarantee that my line is really precise by following that same pattern again. Come on. Adding my arrows to show that it's infinitely continuing in each direction. And again, I have a third line with a slope of 1/2. I had rather hoped that we would finish this lesson today, but it's clear this is going to take a second day. So let's just pause here and we'll finish this in a second video in a second day. Thank you for watching. We'll see you next time.